Okay, so we're going to start with separable equations and solutions to start our course on differential equations and linear algebra. And these are the goals for this particular lecture. We'll talk about what is a differential equation, how to solve separable equations, implicit and explicit solutions, initial value problems, which generally will be abbreviated IVP, general and particular solutions, and how to check if something is a solution. So what's a differential equation? Well, it's just an equation like this. It's an equation that involves a derivative. And a first order differential equation just involves a function and its first derivative. And you've seen sort of things like this in calculus. This, in fact, is a calculus problem. The derivative of y with respect to t is t squared plus cosine t. What's y? Well, you just integrate both sides. Generally, I use t as the independent variable instead of x, so dy dt instead of dy dx, because we're going to use x and y later when we look at systems of equations. So we'll be looking at the xy plane and think about things in terms of functions of t. So how we're going to solve this is we're actually going to multiply both sides by dt to get dy equals t squared plus cosine t times the quantity dt. And now both sides can be integrated. Integral of y, the integral of dy is just y plus a constant. And the integral of this dt is 1/3 t cubed plus sine of t plus another constant. Since we got two constants and they're both, we don't know what they are, and they're kind of arbitrary, and it's a little inconvenient to have too many constants floating around, I'm going to gather both of my constants together on my right side and just call it plus c. There we go. So there's a solution. But we have an extra condition, which is that y of 0 equals 1. So the 0 is telling me that t equals 0 and y equals 1. That allows us to find c, right? That's what that condition allows us to do. So if we plug in t equals 0 and y equals 1, we get 1 equals 1/3 0 cubed plus sine of 0 plus c, or 1 equals c. So our solution at the end of the road is y equals 1/3 t cubed plus sine of t plus c, plus 1. And this is a function that has the right characteristics. It has this as its derivative, and it fits this initial condition. When you plug in t equals 0, you get 1. So this is an example of separable equations. You can get all the variables on one side and all the other variables on the other side. So here we got all my y's on one side and all the t's on the other side, and then we could integrate. So generally, a separable equation will end up with g of y dy equals f of t dt, and then you can integrate both sides. So here's an example. dy dt equals 2ty squared plus 2y squared. So I can rewrite this by factoring the right side a little bit. I can factor out a y squared, and I'm left with 2t plus 2. Multiply both sides by the dt and divide both sides by the y squared. And now I've separated my variables. I've got all my y's on one side, dy over y squared, and all my t's on the other side, 2t plus 2 times the quantity dt. And now we can just integrate. Integral of dy over y squared is minus 1 over y. Integral of 2t plus 2 is going to be t squared plus 2t. And we'll need a plus c, and we'll put it there. Technically, you get a plus c from both integrals, but they're arbitrary constants, so we'll just gather them on one side. Great, but we want to solve for y as a function of t. So if we take 1 over both sides, we get minus y equals 1 over t squared plus 2t plus c, and finally y equals minus 1 over t squared plus 2t plus c. Okay, so there's a solution. And it depends on whatever the initial condition is. We didn't specify an initial condition, and that's fine. We found a function that when you differentiate it, it satisfies this equation. So, oops, this should be 3. How do you solve a differential equation using separation of variables? Separate the variables, integrate, and solve for y. So when we integrated, that's where we got this solution. And after we solved for y, that's where we got this. Same equation, we just solved one for y. So generally, after you integrate, you get something called an implicit solution, right? It's an equation that involves the two variables, but you've gotten rid of all the derivatives. So this is an implicit solution. Y and t are related to each other. There's no derivatives involved. Explicit solutions means that you actually solve for y. So this is the explicit solution. When you do separation of variables, you get an implicit solution, then you solve for y, and that give you the explicit solution. Sometimes you can't actually solve for y, and the implicit solution is the best that you can do. And we're often interested in domain and range, right? When we look at this kind of either this explicit or the implicit solution, what can t be? What can y be? Okay, so initial value problems, that was example 1, a differential equation that involves, when you solve it, you get a plus c and an initial value y of 0 equals 1, which allows for a solution for c. Generally, if you have a solution with a plus c, a square parameter in it, that's called a general solution, and a solution where you've evaluated the plus c is a particular solution. So both of these here, these are both general solutions, because they've got this plus c in them somewhere. This here is a particular solution because we've evaluated for the plus c. So that's just some language. Okay, so solve the following initial value problems. And the question is what are the domains and ranges of the solutions, sketch graphs of the solutions, and check the answers with GeoGebra. So this is the same differential equation that we just solved here. So we know that this is the solution. So we'll put the solution here. The general solution is y equals -1 over t squared plus 2t plus c. And then these are the initial conditions. We've got 3 initial conditions. And we'll call this equation 1, equation 2, and equation 3. So generally, we're having t equal to 0, and we're changing y around a little bit. So when t equals 0, y of 0 equals -1 over c. So problem 1, we get 1 equals -1 over c. So c equals -1. And for problem 1, we get y equals this formula with c equals -1. So -1 over t squared plus 2t minus 1. What's the domain of that function? Well, you remember how to do this from algebra. Domain is where the denominator does not equal 0. How do we find that? You take t squared plus 2t minus 1, you set it equal to 0. You solve that using the quadratic equation. T equals -2 plus or minus the square root of b squared minus 4ac, which is actually going to be a plus because it's a -1 inside a square root all over 2. And that'll simplify out. This is square root of 8, which is 2 square root of 2. So all the 2's cancel, and you're left with -1 plus or minus square root of 2. And it's roughly square root of 2 is about 1.4, -1 minus 1.4 is -2.4, and -1 plus 1.4 is about 0.4. So the domain misses these 2 points. What does it look like? The graph. Well, we'll see a picture of it. we'll look at GeoGebra, but there's going to be a question about the domains. Question 2, right? Y of 0 is -1 over C, and we're saying that Y of 0 equals -1. So C equals 1. And what does that make? Y -1 over T squared plus 2T plus 1. And we know how to factor. So the domain here just is all T that are not equal to -1. Right? And then finally, for the last one, for part 3, what do we have? Y of 0 is -1/4. So C equals 4. And that gives me Y equals -1 over T squared plus 2T plus 4. What's the domain of that function? Well, T squared plus 2T plus 4 equals 0. Whenever the T holds that, then that's going to be not in our domain. And T is -2 plus or minus the square root of B squared, which is 4, minus 4AC, which is -16 all over 2. That's less than 0, so only complex solutions. And that means that the domain is all T's. So what's the upshot of this? You see the initial condition actually tells you a lot about the domain. It can have a huge effect on the domain. So let's go over to GeoGebra and see what these solutions actually look like. So GeoGebra is an app, and oops, I need to change the sharing so that we're actually looking at GeoGebra. And if you just type in geogebra.org, where's my sharing? What am I sharing now? I'm sharing GeoGebra. Okay, good. You'll see this, and we can do start calculator, and it'll give you this, and we'll want to know, what do you want to do? What we want to do is we want to solve an ordinary differential equation. So solve ODE, right? What's the derivative? What's the point? So we'll hit enter, and it just gives us that. We are interested in solving 2xy squared plus 2y squared is my derivative. And they use x where I use t. You just have to keep that in mind. And the point we wanted for the first one was 0, 1. And there you go. Here's the formula for the solution. And here's the graph, right? And so that's pretty nice. We can change this around a little bit. What was the other initial conditions we wanted? One was with -1. And that gave us a graph that looks like this. This is our solution. And then finally, the last one was just -1/4. And this should have no vertical asymptotes at all. And it doesn't. And there's our graph. So we can check your work, right? There's the formula for the solution. And you can get a nice graph that'll tell you some stuff about it. So what we can also do is we can also say, well, what is the, how does this actually depend on C? So we'll go over to tools and we will ask for a slider. I'll put it up here and we'll say, okay, well, C equals whatever, run from -5 to 5. So there's a slider. So we'll go back to algebra. And remember that our C is -1 over y0, or y0 is -1 over C. So we can ask to solve ODE. Oh, shoot, wrong thing, delete. You have to hit enter. I'm used to Excel, we hit tab to complete a command. Solve ODE, and we want 2xy squared plus 2y squared. And we want the point to be 0, 1 over c. And that would be our curve. Great. So as we vary c, what do our graphs look like? So c getting bigger and bigger and bigger, you get graphs, the solution to ODE looks like that. And as c gets smaller, if your constant gets smaller and smaller and smaller, what does your solutions look like? Well, this part up here gets smaller and smaller and smaller and smaller. And then boop, end up with this. So the value of the initial condition can vary your solutions quite a lot. Okay, so we'll just stop this. Get rid of that and that. We'll go back to 1. And there's our solution. Now, the initial condition we had was 0, 1. And so what is the actual solution to our differential equation going to be? What's the domain? And it's actually, we only want this middle part, not the two things on the left and the right. So why would we want to do that? Let's go back to our lecture notes. So the solution to this, when we drew it, on GeoGebra, the solution looked like this. We had 2 vertical asymptotes. The vertical asymptotes were at these 2 points here, -1 plus square root of 2 and -1 minus square root of 2. So if I call these 3 separate pieces, I'll call this one function of t, f of t, g of t, h of t. What we want to be able to do is to say that we have exactly one solution to this differential equation. If I take this side and just move it up a little bit, so f of t plus 5, say, then the curve that consists of this side, the middle part, and this side, h of t, is also a solution to this differential equation with the same initial condition, because we haven't changed the slopes of anything, we just by moving this part of the graph up. And we haven't changed the initial condition because we haven't changed the middle part. But it's also a solution. And we don't want that. That gives us infinitely many solutions as we move the left and right sides up and down. So solution to this has a domain only for the middle part, -1 minus square root of 2 less than t less than -1 plus square root of 2. It's just this part of the solution that we want, and not these parts, because we can move those independently and then generate infinitely many solutions. We want to be able to say every initial value problem has exactly one solution. Okay, finally, how to check if something is a solution. You verify it's a solution by plugging it in. So is this a solution to that? Well, you calculate the left-hand side, right? What's the derivative of k e to the 2t? That's 2k e to the 2t by using the chain rule, and k here just stands for constant. The right-hand side of that equation, k e to the 2t, you plug that in for y, and you get 2 times k e to the 2t equals 2k e to the 2t. And so my left-hand side, my right-hand side are the same, and so those are a solution. It's a general solution to this differential equation. To be a particular equation, though, you have to satisfy both of these conditions. So is 7e to the 3t a particular solution to that? Well, we'll take the left-hand side and replace the y by 7e to the 3t. Use the chain rule to get 21e to the 3t as a solution. The right-hand side for the differential equation, we take 3y, replace the y by 7e to the 3t. We get 21e to the 3t. So that's good. This part, this is a solution to that. Does it fit the initial condition? Well, y of 0, using our formula, if we plug in t equals 0, is 7. That does not equal the -7 that we required. So not a solution to the initial value problem. So to solve the initial value problem, you have to solve the differentiable part, but also the initial condition. Okay,